good Easter, good weekend. You're around here, the weather was lovely on Monday. Today, we're going to talk about multivariate transformations a little bit. We won't be doing too much of this ourselves, but it's an extension of the methods that we've done and kind of a bridge to things. We'll look at a few distributions that come out of the normal. We've been doing transformations. If you have a normal sample, you often take the sample average, sample standard deviation, and what do those distributions look like? Those are some of the core distributions that are used in statistics, statistical testing, hypothesis testing, confidence intervals, so we'll do a little bit with that. There's homework 10 on chapter 7 that's due Thursday. The material to do that was really what we did before break, the Tuesday, Thursday before the Easter break. So let me know if you have questions on that. Office hours, regular office hours today and tomorrow. So if you have questions, let me know how that goes. So the multivariate ones, this is in 7.7. So there are different ways of handling transformations of random variables in multiple dimensions. This one focuses on 2 dimensions to go beyond the one-dimensional things that we did. Like a one-dimensional transformation, taking the square root, taking a log, taking 1 over that variable, maybe a linear transformation. I've already seen a few ways of dealing with that. X1 and X2 are random variables. For some transformations, like adding them together or taking the difference, linear combinations of these, if they're independent, you can do a lot with momentary functions. But if they're not independent, then that doesn't work. That would be the joint probability density function. And we're going to consider taking two functions here that transform them, and we're going to consider one special example. We're going to consider, say, multiplying the 2 numbers together. And then y2 is some other function that you might be interested in. So maybe you're interested in a ratio or difference or some other thing. If you're interested in primarily the product, one thing that is done is that this thing often gets left alone and not really changed. So we're going to find the joint distribution of these things together. One is trivially what we had before, but then we're going to integrate that out and get rid of it. And we're going to be left with this product that we really care about. But that's an example of 2 transformations. ID ratio, the book has some other examples there. That's really our interest. If they're independent, you can multiply those together. We're going to look at the densities are simpler. So if x1 and x2 are independent, then the density of the 2 together is just going to be the product of the two things. So we're going to use that. But what we want to know is the density of these 2 things. And y1 and y2 are not necessarily independent, so they don't necessarily factor. You can't do just each one at a time. All right, so kind of motivate this example, we're going to look at one example, or modified example from one of the problems in the book. In problem 7.46 is like this, but we're going to have some substance, some material, and we're going to measure it. Right? And some of that material is going to have a certain amount of copper in it, so it can be dust or rock or something like that. So x1 is going to be the proportion of our object that is solid copper. And the density for x1 is going to be 6 times x1 times 1 minus x1. Or 0 less than equal to x1 less than equal to. So the proportions are going to be scaled between 0 and 1. This is actually a particular beta distribution for this example. This one would actually be, x1 is actually a beta distribution, and the parameters would be 2 and 2. Because it has alpha minus 1 and beta minus 1, so 2 would have to 2 and 2. The second variable, x2, is going to be the proportion of the copper that is of a certain type. Apparently there's different types, different sources. But this works out, so x2 is going to be the proportion of the copper that is type A. And that this is described in the book, right? So that's going to have a different distribution, and we're going to use this thing as a distribution of probability density that would match the proportion across different samples. So this is an x2 cubed. X, the proportion, it's a proportion again, so it's going to be between 0 and 1. So x2 is again some beta distribution. If x to a power 1 minus x to a power, but that goes away if the power is 0. So this one would be a 4, 1. That would be the particular beta distribution for this one. And what we're going to be interested in is in that first variable, x1 times x2. So if x1 is the proportion of solid copper, and this one is the proportion of the copper that is type A, this high quality one, right? Then the product, proportion copper, proportion that's type A, would be the proportion type A copper out of the entire thing. So you have some material, that would be the proportion out of all the material, not just out of the copper, but out of all the material that's type A copper. So this is the thing that we're interested in, is the proportion type A copper overall. And so we want to know what's the distribution of y1 on here of that variable. So we want to know means, variances for probabilities for the amount that we're going to get, proportion of the material that we're going to get out of this different sample. If these two things are independent of one another, then the joint density of the x's would be the product of those two things, the f of the x1 times the f of x2. For this first and second one, if you multiply those things together, you're going to get 24 x1, 1 minus x1 times x2 cubed. But we want the distribution in terms of the y's. So to make this work is we're going to find the inverse transformation that takes our new y variables back to the x's, and then differentiate partial derivatives. And so we're going to evaluate the x density at the transformation point, and then multiply on this extra Jacobian, this extra bit from changing the transformations. That's the two-dimensional equivalent of the one-dimensional thing we did before. So if y1 is the product, and y2, for convenience, we just take it to be one of these, this inverse is easy. x2 is simply just y2, it's 1 to 1 there. But what's the inverse? How do we get a value of x1? If somebody gives you values of y1, y2, how do you figure out what x2 is? I mean, what x1 is? Well, just the ratio of these two things, right, will give you x1. So written in terms of y, so you take y1 over y2, it should give you that same value. So if you give me y1, y2, and I want to solve for x1 and x2, that's the solution to do that. We're interested in this one really as our only primary outcome. Let's do this two-dimensional transformation, two variables over to two variables. We keep track of both of them. Right? So the joint density of y1 and y2 is related to the density of, these are the y's, and this is the joint density of the x's. It's the joint density of the x's at these transformed values. So x1 would be at y1 over y2, and x2 would, just a one-to-one thing there. But there's a scale change. Right? This is all involved in a scale change. Yeah.
Would it be y1 over x2?
Well, if you divide it by x2, right? But in terms of y, is that, yeah. But you're right. If you divide x1 over x1, x2, divided by that one, right, it cancels. You just get the x1 you want to get the inverse. Right? But you write those in terms of the y. The thing that gets multiplied on there is related to the scale change. And in the two-dimensional calculus, we're going to take partial derivatives of this thing and then take the determinant of that. In this course, we're not going to go into all the math to explain why exactly that works. Right? But we took the single derivatives when it was 1, and the generalization of that for 2 is looking at the change in 2 dimensionals at a time. So if we differentiated this thing with respect to y1, we just get 1 over y2. If we differentiate this with respect to y1, well, it's not in there, so it's just 0. And then we differentiate this thing with respect to y2. Right? So it's negative y1 over y2 squared. And then we differentiate this with respect to y2. And so that's 1. This is something called the Jacobian. The determinant of that, the determinant of a matrix is the product of 2 by 2 matrices, right? Is the product of this product minus this product. So it simplifies to just 1 over y2 in this case. We actually take the absolute value just like we did in the one-dimensional case, but all of our y's are positive. So that's it. Right? And this extra little piece goes on to here. So that's the source of this extra little scale change piece. I'm distorting space by, that's getting too much into the geometry of the math for it. So what does this work out to be? Right? Well, our joint density of these two things, if they're independent, right, then it's the first one evaluated at this, and then the second one evaluated at this one, and there's extra y over 2 over here. So this density for the x's, well, when we put them all together, there was a 24 out here. And then there's an x1, which is this one, times 1 minus x1. And then there was a x2 cubed, and we're putting the y2 in there. And there's an extra 1 over y2 down there from the Jacobian, from the derivative parts up there. You can simplify this a little bit. You can cancel one of those and multiply both of the parenthesis pieces by a y2 and get 24 y1 times y2 minus y1. Now, that's the joint density. There's a little wrinkle that comes into this, right, that what's the range of these two things here? Now, x1 and x2 went between 0 and 1. In principle, y1 and y2 can go between 0 and 1. Right? Take two things that are between 0 and 1, multiply them together, you're still between 0 and 1. However, what's the relationship between y1 and y2? Is there any link here between these? Which one of these two things is one of those bigger or smaller than the other one?
So y2 is always bigger or equal to.
Yeah, this one always has to be bigger, right? Because you're multiplying by another thing that's between 0 and 1, so it's going to make it smaller. So the density, the y1 is between 0 and 1, and y2 is between 0 and 1, but y1 is less than or equal to y2.
Can't y2 not equal 0 because it's in a denominator?
It's in the denominator. So yeah, I mean, so the beta has basically 0 probability at an endpoint. So you could write it as not including that to avoid an appearance that that would, right? So if the beta densities don't include probability add 0 and include 1, that would be, avoid the appearance of dividing. You don't want to divide by 0, right? So when we have a joint density, what did we do to find the marginal? Right? We integrated out of one of those points, right? So to get just y1, remember just y1's our interest. And 2 variables, transform them into 2 variables. And now we can integrate out that y1. So the density for y1, for the one we want, right, this is our goal, to know what this thing is. We're going to integrate out the joint density, which has 24, y1, y2 minus y1. We're going to get rid of the second one, integrate out the second one, to go from the joint to the marginal. So the little wrinkle is because these two are related in their range, y2 can go up to 1, but it can't go below 1, the first one. Right? The first one had to be smaller. The first time I did this, I integrated from 0 to 1. You get something that could be negative, but you can't have negatives for a density, so I had to think about it. Like, why did this work out? But because the way they're set up, they introduce this little dependence. So if you integrate this thing out, there's 24 y1, and this is to y2, so you get a y2 squared over 2 minus y1 times y2. And you evaluate that at y2 being between the lower point it can be and then the top. If you plug in y2 for that and do a little manipulation of it, I'm not showing you all the algebra, but it can be written as 12y1 times 1 minus y1. So that ends up being the probability density for y1, which is the proportion of all the material that is this type A copper that they're excited about. And what does that look like? You have something between 0 and 1, and 1 minus that in there. It looks like another beta. It turns out that this thing is another beta distribution. And it would have to have parameters 2 and 2. So we started with x1 was a particular beta. Oh, y2, x1 ends up being the same thing. Wait, what is that? 6. Do I have something wrong with the math, maybe? 12, we have another one that has to cancel out. 2, no, there's a square, sorry, there's a square. That's what it is, I forgot that square, so beta 2, 3. Right? The first time I thought they were different, and they are different. There's a square in there once you put everything out and work it out. Right. So we started with something about the proportion of solid copper overall. It was this beta, the proportion of copper that was type A. You know, this had an average, the average is 4 out of 5, so about 80% of it is solid copper, of type A of the copper. So you put these two things together, you're looking at this product, and the result ends up being from this, this is the step, that proportion of type A copper overall has this distribution, right? So the average of y1 from a beta distribution is 2 over 2 plus 3. So that's 4 out of 5 or 0.4. So for that thing you're interested in from those two variables, we've got a new one. The beta tells you, the average probabilities and all that stuff, right? So we can use some of the calculus and so on to get the distribution of a new variable. But any questions? Yeah.
So we kind of glossed over the calculating of the Jacobian pretty quickly. So if we
Yeah.
saw another problem like this, would we be given the Jacobian in order to?
Yeah, so
Work out
if
the
you're
math.
given two functions here, you find the inverse, the way to do the inverse of those, and then take partial derivatives, and then take the determinant of that and absolute value of that, yeah. So the plan isn't not to give you problems like this to do, but stick to the one-dimensional ones to do. The book in that section has another couple examples that do this. But that's, I wanted to give you the nature of the, how you can get from a pair of variables over to the other. As a way of bridging into saying something about distributions that you get from the normal, right, from larger samples. But this is one concrete place where it works out. And the other ones in the book give you some other ones that work out. A next level course in probability would do that with a lot of different circumstances and show how different variables are related to one another and different functions of variables produce interesting things that get used in applications. So yeah, a next course in probability would do it much more intensely. But we've done the univariate one. We've fully done that. And this is at least an example that you can go two variables to other and you do certain procedures to make it work out. Any other questions? So that's graduate school in statistics or probability would use the really use all 3 semesters of calculus and some more and some linear algebra as a basis for it. Right. So things are kind of similar for n-dimensional transformations. So if you have variables x1, x2, up to xn, a sample of size n, random sample, and you have an n x1, x2, up to xn. It's a distribution of all the values that you would measure in this set of n observations together. So you have 15 people, you're going to measure their heights, you're going to measure their speed at doing some activity, and so you have n measurements, 15 measurements, and it has a joint distribution. They might be related to one another, they might be independent, but there's this joint density. And one summary, for instance, we might do is the sample average. This is 1 over n, the sum of I going from 1 to n of the xi. And ultimately, we want to know what's the distribution of the x bars. What probability distribution does x bar have if you've had a random sample from a certain distribution or in measurements? So the analogy, right, to doing that individual transformation, because if you let one variable equal the average, we can let the others not exactly be the other ones, and we then can find the inverses for it. There's so for instance, all these others, well, we won't write those out, but it's the same process, the inverses, that Jacobian thing, and so we'll ultimately go through the process by giving the joint distribution of all of these things, and then integrate out all those others, do a multidimensional integral, get rid of all those others, and in the end, you'll end up with just a marginal distribution of this. And in many cases, so that would kind of follow the same procedures, but in a multidimensional case is one way to actually show what that distribution is. If these things, again, are these x's that we have, if these different x measurements are independent of joint distribution of all of our x's conveniently becomes a product. The density for the first one, the density for the second one, the density for the last one, etc. In different things, you can do that. Now, if things are independent, and we have certain distributions, instead of going through this calculus procedure, we've seen that sometimes we can use things with moment-generated functions. And so it provides another way to do certain functions. Other functions, not the average, not linear combinations, wouldn't work with moment-generating functions. But if the x's are independent of one another, and the function that we want is a linear combination, then using the moment-generating functions in GF method could be easier. So in particular, let's consider an example where it works out. Let's say that x are values, x and y, each one follows a normal distribution. Some mean and variance. I and 1 of n. And they're all independent of one another. What is the distribution when you add them all together? That's the sum. And what's the distribution when we divide that sum by n, and that's our sample average. Start out with a normal distribution of measurements, take a random sample, independent measurements, and then average them together. Well, the moment-generating function of a sum of independent random variables that all have the same distribution is the product of the first one times the second one, and so on. And if they're all the same, then it's the one distribution for the original x measurements raised to the nth power. And if you transform something by multiplying it by something, the way it changes the moment-generating function is it takes the moment-generating function and you end up with a t over n there. And so combining those things is the moment-generating function of an individual one, evaluated t over n raised to the nth power. For normal, what was the individual moment-generating function? For normal, the moment-generating function was e to the mu t plus sigma squared t squared over 2. That's for one observation. So for the average again, you put that together. Well, let's do it in 2 steps. U t over n plus sigma squared t squared n squared, and there's a 2 down to the denominator. And all that's raised to the nth power. But when you have something to another exponent, it's the same as multiplying across. So raising this n up here, effectively you can just multiply this by n, and the whole thing becomes e to the mu t plus sigma squared t squared over something e to the something times t plus something times t squared over 2. So the conclusion is that our sample average, x bar, when we had a random sample from this normals, random sample of different normals, has a distribution that again is normal. Its mean is the same. No change in the average. And the variance then is sigma squared over n. Here's the mean mu, and here's the new variance for that. So it's a distribution that becomes more centered. So when we started out with a normal sample, this distribution of x bar is one of the distributions that comes out of that distribution through transforming it, through taking this to their average. We've seen some results like this in terms of means and variances, doing it similar. We've done something like this before. Let's look at an example. Does everybody have a copy of the handout? Right. So the context for this, it's just Easter. If you look up on the Wikipedia about rabbits, right? The New England cottontail rabbit, adult males, have a range that is about 1.4 acres on average. The territory that a rabbit covers, about 1.4 acres. Adult females, about 1.2 acres. Things are different in different places of the country. And there's a study in southwest Wisconsin where the average was more like 6.9 acres for an adult male. Much more spread out, much more rural, and a lot more. So I chose just one of these, picked one of these, the male one, but you could do this with the other two. Let's say that the amount of home range that one of these rabbits has, suppose it's normally distributed with about 1.4 acres on average, and a standard deviation that is 0.3 acres. If you convert this to square feet, an acre has about 44,000 square feet. That's what I recall, that's what I used anyway. So this ends up being about 62,000 square feet as an average. And the standard deviation would be 13,200 square feet of space. Now imagine you're tracking rabbits. You catch them, you put collars on them, so you track their movements, and after a month you make a map and calculate the area on that map to get the amount of home range. Consider different scenarios. What would it look like if we just had one rabbit? What would it like if we would have 8 rabbits? What would things look like if we had 32 rabbits? Or if we have a big study, we actually get 128 rabbits. So let's simulate it. We could write down the distribution. Right? If these are really normal, if these rabbits really are independent of one another, so we might need to have them, separated for a while, because if there's 2 male rabbits overlapping, there's going to be some conflict, right? And some interaction, and one's probably going to take more than the other. But in R, we can simulate these things. So here, set a random number seed for today's date. To generate 1,000 values, this would be as if you had 1,000 individual rabbits. Right? And each one had this mean of 303,600. Why is that one? Why did I use that one? Ooh, okay, I didn't use the, what I did is in Wisconsin, I used the Wisconsin numbers. So in Wisconsin, it was more like 6.9 acres on average in the study. So I simulated that one. So we're going to do this differently. At 6.9 acres ends up being 303,600. If the standard deviation of this one, sorry, I switched. If the standard deviation is 1.2 acres for the rapids in Wisconsin, I think I had intended to do the ones in New England, but somehow my mental is kind of going through the flow of the morning. I switched to that one, so that's the one I simulated. Put in the code. The standard deviation is 52,800 square feet. So these numbers are going to be bigger. So that's the individuals that are simulated with n equals 1. So that's corrected. And we do a histogram of those. All right, the histogram of, so x is simulated that way. Right. The histogram of x looks like that. So roughly normal. If I make 40 bins and set the limits a little bit more, and put a vertical line at the average, right? Our normal assumption says the data is going to look like that, right, approximately, and so it's mostly more normalish looking, right, around there. A QQ plot is pretty nice and straight. But what does it look like if we take averages of size 8? So taking a sample of size 8, right, 1,000 different samples of size 8. So a quick little way of doing that is to imagine catching 8,000 rabbits and looking at them, and then putting them in a matrix that has 8 rows, 1,000 columns, and taking the average across each row. And this little one line does that. And if I change the number of rabbits involved, I get bigger samples. Right? So here's a histogram for the averages of 8. Right? And it's set with the x limits that are the same as before. So that impact of taking the averages of 8 makes everything much tighter. Right? The range is much less. But it's still normal. If I redo it but don't put those x limits on there, it's going to stretch out in the graph to basically be this range of the actual number. So when I run that again, this is the histogram of x8, but now it's stretched out for its full range. Pretty much normal. And that looks pretty normal as a straight plot. If we take 32, again, it's more narrow. Right? We quadrupled the sample size, so variance goes down by 4. Standard deviation, which is the square root of that, which is what we really see, goes down by 2. So it's more narrow. Again, it looks pretty normal, pretty straight. And here's 128. It's even more narrow. The averages aren't going to be very, very close. But if you look at it on kind of the expanded scale, you mostly have normal. There's kind of one point popped out here by chance. Right? And it pops out here as one out of my 1,000 averages. Each one had 128. I happened to get one sample that was pretty unusual. I don't know what the individual, I didn't save the individual values that went into it. So I don't know what caused it to be particularly low. But mostly they're aligned with the normal with one peculiar outlier. That looks extra low. So part of the point of doing these transformations to get new variables is sometimes you're interested in something like the proportion that of the type A copper overall, and you have two other distributions that you can work with so that you can transform to get the thing you actually want. Another big thing is to deal with these statistics, these X bars, the sample averages. And if they're normal, right, you can go through the Jacobian thing and it works out, or moment generating function is kind of a little quicker way to see it. But it becomes a new normal distribution. So if the xi are independent, often we write IID if they're all the same distribution, normal with the variance of sigma squared. Then the distribution of this sample statistic is still normal, same mean, but now the variance has gone down. A second common statistic to report is the sample variance. Right? Usually we don't know sigma squared, right, except by estimating from data. And so we have a second statistic is S squared. S squared is 1 over n minus 1 times the sum I equal to 1 to the n of xi minus x bar squared. And so we can wonder, what is the distribution of that? This is again a transformation. It takes our n values of x and it reduces it to one number that summarizes the values. In general, if the x's are more spread out, you get bigger sample variance, right, bigger measures of heterogeneity. If they're all close to the x bars, it's small. So across samples, you know, the rabbits that are in the Northeast are going to have small standard deviations of a sample, whereas the ones out in Wisconsin or other places where they're, you know, it's vast, probably the ones out in the desert, maybe they would even have bigger ranges because it's much more sparse in getting food and things like that. So in statistics, this is called sample variance. And S squared is called an estimator of this population variance, sigma squared. So this S squared is the sample version, and this is more the population, right, or theoretical one that describes the probability process. Most of the time in this course we've been using that one, giving a value to it, and then doing calculations of one sort or another. But in statistics, we often, right, want to know what that is. Why is this one used? Why is that n minus 1 there is used there? Well, it turns out, you know, so let's say that the expectation of each xi is mu, and the variance of each xi is sigma squared, so that the expectation of xi squared is the variance plus this thing squared, right? So variance of xi plus the expectation of xi quantity squared. And the expectation of x bar, we know it's mu, and the variance of that one is sigma squared over n. So the expectation of x bar squared is its variance plus its expectation, so it's sigma squared over n plus mu squared. If we wanted to figure out the expectation of s squared, what is the average value of that statistic? Well, it had a n minus 1, so that can be pulled out. And this term, the sum of xi minus x bar squared, can actually be written as the sum of xi squared minus n times x bar squared. So if you expand those things out in group terms, it kind of combines. So taking the expectation would be expectation of the sum of these things squared minus n times the expectation of x bar squared in there. over n minus 1, the expectation of it 1 xi squared is the sigma squared plus mu squared. But there's n of them, right? Each individual has that one. So there's an n times that. And then the average of x bar squared is that thing there. That's why I wrote them out there. And so the mu squared go away. They cancel. And there's a sigma squared. And what's left, you can pull out, and well, what's left is an n minus 1. And that cancels that. So if you cancel everything out, it ends up being sigma squared. So that n minus 1 is used in traditional statistics because the average is s sigma squared, called unbiased, right, for that. But what is the distribution of s squared? What's its actual distribution? Not just its mean, but what's its variance, what's all its other moments, what's the plot of its distribution. We can work that out, but let's look at kind of this simulation. Right? We can simulate that as well. So we're going to start back at the same number seed, get our x's. You know, we had 1,000 values, 1,000 different rabbits from that distribution. 5280, that thing squared is a huge number, right? The variance of 1,000 different values is again a big number. It's off from that slightly, but you know, not hugely off. The standard deviation is on a scale that's a little more relatable. 51,000, whereas the value that went into the simulation was 52,800. So it's a little bit lower, but kind of in the same range. Right? These three lines calculate, generate these different samples. But what am I doing here? Instead of taking the averages, I'm taking the variance of every single row. So variance of 8, variance of 8, variance of 8 in the first case, or variance of 32, variance of 32. What do the distributions look like? And if you do the histogram of those, it's skewed, right? Some type of skewed distribution. Here's where the variance, the square of the standard deviation for that example really would be. So it's in the middle there. If I take this histogram of 32, it's a little more narrow, a little skew again. That point's still in there. If I just do the plot on the range of the data, not the range I had for comparability, it looks a little skewed. Not quite as skewed there, right, but a little bit. Right? If I do 128, it's more narrow again. That sample size is getting, my sample variance is getting closer and closer to my actual variance. And if I, this other plot, right, looks almost normal, right? Here's, where we'll talk about where we use that in statistics. So if we had, say, these 5 values, the standard deviation of just those 5 values is about 0.28. Anyway, we'll come back to that numerical example. But what is this distribution of sample variances, right? So we get at that. So the question is, what is the distribution of that squared, of that sample variance? What is its probability distribution? The book lays out some work in here on over a couple pages. We're not going to go through all the details, but you can read some of that there. It turns out that a scale version of this thing, the value of s squared scaled by the actual variance, with that on there. So what is that? This function is actually the sum of the xi minus x bars squared over sigma squared. be written as, if you bring the x, that in there, xi minus x bar over sigma squared. It's almost like standardizing, right? So if we z-scored things and took xi minus mu over sigma, then the zi has a standard normal distribution. We're not exactly at that point because it's if you square a standard normal, it turns out to be a chi-squared distribution. Something called chi-squared with 1 degree of freedom, which is a particular gamma distribution. In our book, we do 1/2, 2. So if you started with a univariate normal and square it, we could use our PDF method or our CDF method to get that it follows a certain gamma distribution. Right? So within the scope of the course, we did this type of work that you have to do an x that's normal and standardize it, you get a standard normal. If you square it, you get a particular gamma distribution, which was also called a chi-squared. And if you add together gammas, if you do a sum of the zi squared, or I going from 1 to n, so if you have n observations and they're all normal, you standardize each one, square each standardized version, and add them together. Right? And this thing ends up being a chi-squared with n degrees of freedom, which ends up being a gamma distribution, particular gamma distribution. We don't quite have that because we're not subtracting mu. We have to estimate mu. We're subtracting x bar. But it works out that what we lose is 1 degree of freedom. Distribution called chi-squared with n minus 1 degrees of freedom, which is equivalent to a gamma with n minus 1 over 2 as the first parameter and 2 as the second parameter. And this chi-squared is in R. There's R chi-square, for instance, will give random values of chi-square, or d of chi-square will give the density, or p of chi-square will give the probability it's less than things, or q of chi-square will give certain quantiles. So this is a familiar distribution that works out. We end up losing, this decreases by 1 as described in the book, because that x bar is stuck in there instead of knowing mu. It kind of takes away one independent deviation. If you know x bar, and all the deviations add up to, from x bar add up to 0, there's not n of them really, there's n minus 1. That's one way of thinking about it. So you get this particular chi-square distribution. What does chi-square look like? Chi-square distribution looks like this. So chi-square distribution, the sum of degrees of freedom, is a positive random variable that goes up like this. On the handout is an example of a chi-square table. It's on the back of the first page. So, this table is so in statistics before a lot of computing, before we had calculators that could calculate as much and hold all this information or anything, right? That tables of books were published. It was a lot to do computing to great precision when you had a complicated density function and needed to integrate under things. So companies would produce these things, and so this is the chi-square table. It's from a book by Bernard Brazza that we actually used for the 140 class. And So this D is the degrees of freedom. So n minus 1 would be on this one. So if we had eight rabbits, right, we would look on 7. And this is the 50th percentile. So the 50th percentile of adding up those square deviations is about 7.34. And here's the 75th percentile, and so on. These are things describing the distribution. So the chi-square distribution would be like this picture, you know, the median somewhere about here. And you get things up here like the 95th percentile, or you know, the 5th percentile. And that table gives you those different cutoffs that are. So this kind of standardized version of S squared has this distribution. So what's the distribution of S squared? So if you have something that is, you know, this version of S squared, if this thing is chi-squared with n minus 1 degrees of freedom, where S squared then is sigma squared times n minus 1 times y. Multiply both things over there to get rid of that. This thing has a distribution that's called a scaled chi-square. For the scale factor, the multiplication factor is this. That thing. That's what it's called. So that takes the general form of the chi-square, that nice, that kind of skewed curve, right, and spreads it out according to how it would be for that distribution. And so, the expectation of S squared from this formulation, well, sigma squared over n minus 1 is a multiplier. And this thing was a particular gamma, so let's recall that. The way we set up the gamma, the expectation of it is you multiply the two parameters together. It's n minus 1 over 2 times 2. So everything cancels and it's just sigma squared. We knew that, right? That on average our sample variance is this population. What's the variance of the variance? What does that mean, the variance of the variance? As we took samples, different samples of size 8 or 32, every time we get a variance. If we did that across multiple samples, we would get different estimates of it. So depending on your sample, is it more spread out than typical, less spread out than typical? You're going to get big or small values of S squared. And so it has a distribution, so it has a variance. So this is a histogram. Each point that would go into here. Now x8 here is a standard deviation. So if I look at 8, say the first 10 of those values, they're big, right? So maybe look at the 4 so we get them on the screen. So one time the sample variance S squared gave that value. Another time S squared for a different 8 rabbits gave that value in square feet as a variance. You know, big values here. If you take the square root of each of those things, it's not S squared but S, and it's closer to the 52,800 that you know would be easier to think about. So there's a variance of that. So what's the variance of this distribution? If it's really normal with mean variance squared, variance, what happens with variance? This thing gets squared, multiplier out front gets squared, and the variance of a gamma was n minus 1 over 2 times the second parameter squared. So the variance is sigma to the 4th. There's a 2 up front and n minus 1. So this statistic, this thing, we've taken all these in observations and transformed them into S squared. It has an average. It's a new random variable. It has an average. That is the sigma squared parameter we might want to know. And how accurately we will know it, it's related to its variance, right? Variance is a probability distribution. So that's a second major statistic that comes out of transformations of normal samplings. It's chi-square distribution. So we've did a lot of study of individual probability distributions, you know, finding their means, finding their variances, finding areas under the curve probabilities. And then in chapter 7, at the beginning of chapter 7, we really did something with transforming them. Square root or a linear transformation, you want to figure out what the new distribution is. Because you want probabilities and means and variances for that new distribution. And now we're taking a sample size in and not spend so much time figuring out all the mathematical details about how to do it. But one result that would come out of that process would be that the sample variance, if your sample's really from a normal, has this chi-square distribution. So x bar s squared. A third major statistic is called a t-statistic. And so we'll look at that. That's all that. So in this, there's kind of a couple things. It turns out that x bar, so we're going to have some observations, x1, x2, xn, are normal random variables, and they're independent of one another. You map out areas that are clearly bigger than the range of a single rabbit. 1 acre, 640 acres in a square mile. So maybe go every square mile and pick one rabbit. It's very unlikely that they overlap unless you pick rabbits right at the border. Go in the middle of different areas and find rabbits, tag them, monitor them for a month, their movements, and then map out their areas. If you do 8 different square miles, there's very likely that they don't interact and are independent. If the area is roughly normal, right, then you would have that. X bar and S squared under these conditions are actually independent random variables. The mean, the sample mean, and the sample variance from normal samples don't actually influence each other. Other variables it does, right? So Poisson was a count, the mean and the variance were the same. So if the data are Poisson, then those statistics end up being related to one another. The bigger the mean, the bigger the variance. But in normal samples, these are two different things. They don't end up being related. So there's some discussion of this, right? So some discussion of how the PDF function of these two things would factor, and how the moment generating function ends up looking like a product of the two moment generating functions. So anyway, there's a couple of ways of looking at it with techniques that extend slightly things that we've done in the class. And the question in statistics, we're often interested in comparing x bar to some hypothesized value of the mean. Or thinking, if we knew the mean and we could subtract it, what would be the distribution? Instead of standardizing by, do a little preview. If we subtract the mean and divide it by sigma over the square root of n. Why that? Variance of x bar is sigma squared over n, so divide by the standard deviation should bring it back to a variance of 1. This standardized version has a standard normal distribution. If you knew sigma and wanted to standardize your distance is how far is x bar from some hypothesized value. All right, that would be kind of the scale standard deviation. How many standard deviations for x bar are you away from that value? But we don't know sigma in most statistical applications. So instead, we look at a function s over the square root of n, and we plug in our sample value for that. So what is the distribution distribution of t. So to get at this, right, is, you know, the way you figure this out is through our transformation methods. You've got a distribution of x bar, a distribution of s, and you take this ratio and they're independent. It's a bivariate transformation. We did one example of a bivariate transformation. And so the same type of techniques applied to that particular version of it end up giving you the probability result. So if you have the density for x bar, the density of this chi-squared, it's a certain bivariate transformation where you're going to grade out one of them. So it's that same that same process. Right? Or you can view it as you have n observations. You have all your x1, x2 up to xn that are independent normals. You have x bar and s, and then this transformation of that. So it can be an n-dimensional thing to n-dimensional variables and then integrate out a bunch. So there's kind of a couple ways of viewing the whole process. Right? In there. But this t, which is x bar minus mu s over the square root of n, ends up being, can be rewritten a certain way. So there's a sigma over the square root of n there. That's our standard normal. And then if you have a big square root here, if you do n minus 1 s squared over sigma squared, and all of that divided by n minus 1. It's a little funny, like I'm just drawing stuff up there. The thing in the numerator looks like a standard normal random variable. So this one is a standard normal random variable. This thing is the thing that we said was a chi-square. And the numerator, the two parts should be independent. The only random variables really are x bar and s squared. And those two things I said are independent. This thing, a ratio of standard normal divided by the square root of a chi-squared divided by its degrees of freedom, has something called a t distribution. With n minus 1, it's called n minus 1 degrees of freedom. In there, and this ends up being a critical probability distribution for use in statistics. You go through all the mechanisms of doing that. You can show that the density, the probability density function for this t distribution looks like this. It's a gamma. I'll just write it up for the sake of writing it up. So this b being is our degrees of freedom in this case. B over 2, and there's a square root of b over pi. Kind of interesting, the gamma distribution of 1/2 is the square root of pi. It's kind of amazing that it kind of comes out to be that special function. And then there's 1 plus t squared over b raised to the negative b plus 1 over 2. And the values of t that you can have go between negative and infinity. Right? About 0 is this function. Can you tell me anything else about this function? Looking at this little core part. 1 plus t squared over b. What happens as you go on either side of 0? As you go, first of all, it's symmetric. Right? So t squared, you go plus 1 or minus 1, you square it, you get the same value. So this thing is symmetric about 0. And it's decreasing. As you go further away from 0, you get squares bigger and you get a bigger value in here. But it's 1 over that because of the negative. So it's decreasing as you go away. In fact, this thing basically looks like a normal curve. It's another curve centered at 0 that looks very normal-like. The normal distribution is a little bit higher in the middle, and a little bit lower. So this red one is the standard normal. But the t distribution with certain degrees of freedom looks really similar, but has a little more probability out in the tails. The probability that you're out further is a little heavier out here. So the probability you're out here is a little bit more than normal. The chance that you're in the middle is a little bit less. And so that change in probabilities reflects that, here was the formula x bar minus mu s over the square root of n. The fact that you have a little higher probability of getting extreme results reflects the fact that you're estimating the variance instead of knowing the variance sigma. Because this also has to come from the sample. Sometimes it's going to be small, sometimes it's going to be big, bigger than sigma. And this distribution is also what has been tabulated. So on the last page of your handout, is a t-table. This is really just looking at the upper percentiles. So let's look at, say, the 0.975 quantile of your percentile. In the 0.975 column, you go all the way down. Actually, as degrees of freedom goes to infinity, as in a limit, this thing becomes the normal curve. In the limit, it is the normal curve. Right? And so the probability you're greater than, say, 1.96 is there's 2.5% out there. But to get 97.5th percentile of these other t's, distributions are a little bit further out there, reflecting this extra variability. Right. So there's a thing called the t-distribution. It's related to these bivariate transformations. Right? And it's related to, this is a ratio of a normal over a certain transformation of a gamma distribution, which is a chi-squared. You get this thing called t. How does it get used in practice? Well, if you can make probability statements. So the probability that this t value that has n minus 1 degree of freedom, well, under this curve, under this t curve, we could find the points that have, say, 95% in the middle. That is 2.5% out here, and then there's 2.5% left over. Out of the 5%, if we have that's left over, we have 2.5 out there. This point, we call this the 0.025 tail with n minus 1 degrees of freedom. And this is the 97.5th percentile. Not using 95th percentile, because I'm also adding in this extra little piece, I think it's all the way cumulative up to there, with n minus 1. It's symmetric. So the place that cuts off 2.5% there is an equal distance over here. This is actually the negative of the upper cutoff. Right? They're just the minus of each other, equal distance, and it leaves off 2.5%. So the chance that you're less than this cutoff up to this cutoff in probability, just from that distribution, is 95%. that would be just a statement about the t distribution, the 95% or between its, well, this really applies to any distribution, between its lower 2.5% and its upper 97.5% is always 95% of the probability for any distribution, right? And this is just writing it specifically for t. What is t? What is this thing here? This is x bar minus mu s over the square root of n. That's in there. And we can rearrange the symbols a little bit to write a new equation. Actually, it's taking the lower half and rearranging it, and then taking the upper half and rearranging it so that mu is in the middle. Now to write more space. Right, so if you imagine one equation, right, with mu in there, you could solve for mu. And you could do the same thing on the other side. And what you get is x bar plus the t value, 975 minus 1 times s over the square root of n. On the other side, and x bar minus the t 0.975 and minus 1 times s over the square root of n on the lower side. And all we've done is manipulate the things inside, so it shouldn't change the probability content, so it should be 95%. So this is the source of a compensate. And so this lower point, so a 95% confidence interval, for mu is this interval x bar minus the t value, and I'm not gonna write all the subscripts. Maybe I'll just write 0.975 there, and then x bar plus the t 0.975 s over square root of n. It's called a 95% confidence interval for mu. So what gets done in practice in statistics, if you collect some data, you collect your 8 rabbits, you look at it, the data, see is it really kind of close to normal or more or less, not too extremely skewed, right? There's not one super rabbit that's taking up a square mile and a bunch of other small ones that are taking up nothing. And not too skewed, mostly kind of normal. And we want to know where mu is. So we're going to calculate our sample average, our sample statistic, a cutoff value from a t-distribution, a probability-based value from a t-distribution, and calculate that interval, lower endpoint, upper endpoint. Say we're 95% confident the actual value for the average range is in that interval. Right? And that's how scientific statements are made, about from data to the population. So that's an inference, and it comes out of that probability formulation. These distributions coming from normal and our transformation methods that say what the distributions are, and then calculating probabilities. So here in this example, say we had these 8 rabbits. And these are hectacres. That's kind of like the Northeast. It's kind of switched from the Wisconsin, which is more like 6.9, to these ones that are the eastern cottontails up here in New England. Their average, here's the actual x values. X bar is the mean, 1.32. The theory, the kind of hypothetical thing that I got off of Wikipedia describing eastern cottontail racket said 1.4 as an average acre. Right? It's based on a scientific study that's quoted there. The standard deviation of those values is 0.28. What's called the standard error is that standard deviation divided by the square root of the sample size. So 0.0996. That more accurately described as the variability of x bar, right? Like sigma over the square root of n, s over the square root of n, rather than an individual rabbit. What's the variability? The average is that smaller value. That's often called standard error. So here's the x's, x bar, and st. the cutoff for a t-distribution instead of 1.96, so Q norm at 0.975 is about 1.96. But because we're estimating based on just 8 observations, we use 7 degrees of freedom, and our t-value, our multiplier, is a little bit bigger. 2.36 is the quantitative adjustment. So it's going to be about 40% wider, or 20% wider than if you had an infinite sample. If you really knew that, right? So that's the compensation through the probabilities. And so our lower interval is x bar minus that t-value times standard error, S over the square root of n, right? And the upper one is this. So we would say we're 95% confident that the average range of these eastern cottontail rabbits, based on our sample of 8 rabbits, is between 1.09 and 1.56 acres. And that's the result of our scientific study. One of the numbers that's published on that. And so this is a key concept we get to in introductory statistics, is confidence interval and interpreting it. We don't go through the foundations of the probability to build up to this case or anything with actual transformations, but that's the tool that gets used. So if you ever take a course that does statistical methods and they start doing t-distributions, well, it's a normal over the square root of a chi-squared divided by the square root of freedom. It comes from some process like that. And if you get a confidence interval that's x bar plus or minus a t-value times the standard error, right, you get, that's where it's coming from. Now, if we get, they interpreted this, so, just a couple of our book has historical notes, right? So it's called Student's T-Distribution. The original article that described this was just, the author was just a student that, I don't know, in our modern time, everybody, you always put your name for credit for things that you've done. But 100 years ago, 200 years ago, there was often lead people in a laboratory or a study group, and then the students, if they did anything, would either publish under the name of the lead person or be anonymous. And so it was just something by a student. And this t-distribution, it's actually somebody named William Gossett who wrote about this in 1908. By that time, it was more based on empirical observation, that saying that the normal distribution was too narrow, that would make intervals based on 1.96 as the multiplier. Too often they didn't cover. The interpretation of 95% intervals, is that's a 95% probability. What is probability? You're doing something over and over and over again, and it has a 95% probability. You'd expect it to happen 95% of the time. Sometimes it doesn't, sometimes it does. But if it's 95% of the time that it does, that's pretty good. That's pretty reliable, right? And so, but if you look at something over time and it's happening 80%, wow, there's something wrong with the intervals. They're not wide enough. They're not covering the real value. They're either off center somehow, and there's a bias, or they're not wide enough. And so it was, you worked at the Guinness Brewing Company in Ireland, Dublin, right? And they were experimenting with small batches of things, and somehow noticed that it was different, did some mathematical calculations and transformations, and published some results. Right? And out of that came this t-distribution. Right. So in R, there is also a t-test command. So X is our vector of observations, and what this t-test command does for you, called a one-sample t-test. One thing it gives us is this 95% interval, where the likely values of the mean are. It also translates this into a hypothesis test, a test that the real mean is 0. And that's just something else within statistical inference. But because the t-statistic is so big, 2, much more than plus or minus 2 is kind of getting out there in the tails, getting very unusual. This interval is nowhere near 0. 0 wouldn't necessarily be a sensible interest in this case, in any case, right? In any event. So it's gives this thing called a p-value that's very small. So the probability you're actually bigger than 13 for that t statistic value is basically 0. If it were 0, you had seen an average range of, what was it, 1.3 or so, the chance that you would see a range of an average of 1.3, if it really were 0, is basically impossible. So there's no way to believe 0 given the data. But that's it gets used in hypothesis testing. But we've looked at kind of the rationale for the confidence interval. So the t, so out of the normal sample, x bar by itself is an interesting distribution. S squared is an interesting one, and this t, x bar minus mu, right, s over the square root of n, becomes interesting. Or a standardized version of this thing. If you knew sigma and could divide by the actual standard deviation of x bar, that would be a standard normal. But otherwise, there's this t that adjusts for that and gets used in confidence intervals. So any scientific article you look at that says it's doing a confidence interval for a mean, it's doing that t procedure. There's one other that gets used that we'll call an F distribution, which is really a ratio of variances. So if you have 2 independent samples and have 2 separate variances and took their ratio, you turn into something called an F distribution. So there's another probability distribution that gets used there. If you do anything in analytical regression or analysis of variances, also called NOVA, this F distribution, which is a ratio of variances from normal samples, shows up. So there's one more, but that's we don't need to go into details of that one. Any questions about T? The intervals. So now, the interval that we got, right, 1.09 up to 1.56, in this case was successful. We generated data from a pretended normal sample that was 1.4. So our interval actually covers the real value. But sometimes it would miss a little high or a little bit low. We get unusual samples 5% of the time and end up missing. But 95% our intervals would actually cover. And if you have these intervals for different populations, you can compare them and do other statistics and tests. But it comes down to these underlying distributions, which are derived through our transformation methods and things like that. On Thursday, we'll take up the question, what if the data really aren't quite normal, right? Is normal special for actually getting these results? What happens when it's not normal? That's limit theorem. You get large samples, things start to look normal. Or averages start to look normal. So, all right, great, thanks.
Because I won't be here Thursday,
Okay.
10 a.m. So,
All right, well, have a good trip.
perfect. Thank you.
See you at the final.
Thank you.
And feel free to send emails and stuff if you have questions.
Yeah. Thank you.
Thank you. Have a good one. Yep. Yes.
one
Yeah.
more thing. Just trying to get like the
Yeah.
outline of a note sheet together.
Right.
How long is our note sheet going to be for the final? Just like.
Well, at least one page both sides.
Okay.
And then, do you think it needs to be more?
I was just thinking because the first test was
There's
the
one-
one side and then the second
that's
was
the
the
second,
two.
yeah,
So I
right,
didn't
right.
know if we were going to combine those or.
Yeah, something like that. I
Okay.
mean, so the final won't cover everything exactly, so
Okay.
kind of highlights.
Yeah.
And then a little bit more on recent material. So there'll probably be some univariate transformation, maybe some application of these. So we'll do some more problems with that.
Okay. Yeah. No, I just wanted to kind of.
Yeah, good.
Okay, thank you.
Yep.